In this video, I'd like to continue doing some examples of finding derivatives using the chain rule. And if you missed it, this is the second set of examples. The first video covered 7 examples, and the second video will cover 7 more. Let's take this first one. We've got the derivative. We're looking for the derivative of something to the 5th power. And when we apply the chain rule, the outside function is going to be this piece, the derivative of something to the 5th, and then the inside function is that something, the thing that's inside, the 9x to the pi minus 81x. So when I do the derivative of something to the 5th, I'm going to get 5 times that something to the 4th, and the something is this 9x to the pi minus 81x. I'm going to multiply that by the derivative of the inside. That's what the chain rule is doing. We're saying take the derivative of the outer function, that's the something to the 5th, and then do the derivative of the inner function, that's this 9x to the pi minus 81x. Don't be afraid of a pi, it's just a constant. So I'm going to treat it the same as any other constant. If I use this as a power rule, it's going to be 9 times that exponent pi, x to the pi minus 1. And then I'm going to subtract the derivative of 81. X is negative, or subtract 81. Do you see how important these brackets are going to be? Otherwise, it looks like it's only this 9 pi x to the pi minus 1 that's being multiplied, but we want that whole thing. And when I look over here at the answers, it's going to be pretty evident that it's this one, but is our answer that exactly? Oh, it looks like it is just precisely in that form. So it looks like we're done. That's all we need to do. When we get ready for number 9, oh, get ready because this is going to be fun. We have not just 1 or 2, but 3 functions. Because what do we have going on here with this number 9? Do you see that we've got on the very outer piece, we've got the square root. And then, let me go back just a bit, and I'm going to color code this instead, if that's all right. So square root, and then we've got this inner function, this something cubed, and then we've got the innermost, which is the x squared minus 10. And do you see how I've broken that up here? As I do the derivative, I'll do the derivative of a radical, which is the 1 over 2 times the radical. When it's a square root, that is. I shouldn't just say radicals, but 1 over 2 times the square root of, and the of is going to be this radicand x squared minus 10 cubed. I'm going to multiply this times the derivative of something cubed, which is going to be 3 times the something, and the exponent's now going to be 2. The something is still this x squared minus 10. And then the derivative of the innermost function is the derivative of x squared minus 10. That's the easy 2x to the 1, right? I can see that this is going to simplify a little bit, and I can also see that this answer is nowhere to be found. But this answer, let me highlight it. This answer here looks a little suspicious, doesn't it? But how would we get this all the way down to that? Well, let's just break it one piece at a time. To start with, I do recognize that we've got this fraction, right? And in the numerator, it looks like we've got a 3 and a 2. I'm not going to multiply those yet. I'm going to write it 3 times 2. You'll see why in just a minute if you don't already see it. And we've also got in this numerator, we've got an x, and we've got this x squared minus 10 squared, right? This x squared minus 10 squared. Let's make sure we've got all the numerators. I don't need to bother about this 1, but we've got the 3, and then we've got this x squared minus 10 squared, and we've got our purple 2x. In the denominator, we've got a 2, and we've got this square root of x squared minus 10 cubed. Before I write it out like that, do you see what I can do here? Because it's a square root. When there's 2 of them, that can be removed from the square root. So we've got x squared minus 10, and then we've got the square root of the x squared minus 10. So let's see what happens next. We could do some reducing. This 2 over 2 reduces. I'm going to rewrite this green. Instead of writing an x squared minus 10, is it okay if I think of it as x squared minus 10 times x squared minus 10? That's the same thing, isn't it, as the x squared minus 10 squared. So that x squared minus 10 squared is x squared minus 10 times x squared minus 10. And when I do that, look, I can get rid of one of the x squared minus 10s. So what do I have left? I've got this green 3. I've got the purple x. And I've got an x squared minus 10 over the square root of x squared minus 10. Now be really careful with that, because think of that x squared minus 10. What if I do this? What if I write that as a square root of x squared minus 10 times the square root of x squared minus 10, and I'm going to put that over the the square root of x squared minus 10. See how that simplifies also? So what am I left with? I'm left with 3x times just one of the square roots, which is the answer right here in the middle last column. Let's look at number 10. For number 10, the outside function is going to be the tangent. So we'll do the derivative with respect to x of tangent, and then we're going to multiply that times the derivative with respect to x of the inside function, this 3x plus 91 pi. The derivative of tangent. I hope you have those memorized. Did you think of it this way? Secant, if I think secant, secant, tangent, and then go backwards from that, tangent, secant, secant. The derivative of secant is secant tangent. The derivative of tangent is secant secant, or secant squared. So the derivative of this tangent is going to be secant squared. Secant squared of what? That's this 3x plus 91 pi. And I'm going to multiply that times the derivative of 3x plus 91 pi. The derivative of 3x is 3. The derivative of 91 pi is just 0, right? So it's just a 3. I could rewrite this, simplify it by pulling the 3 out. So we have 3 secant squared of 3x plus 91 pi. And I think we'll find that here in one of the answers right there. Let's look at number 11. I'm going to erase part of this. Oh, this number 11, even if it looks a little scary, is probably the easiest problem on this entire sheet, because we're not really even chaining. We could see, and this is where you want to always be looking for, am I missing something obvious? Is there something easy? It's just the derivative of each of these different pieces. And look at those first 3, what do they all have in common? They're all constants. So the derivative of 978 and 3200ths is 0. The derivative of 81 and 9/14ths is 0. The derivative of the square root of 777 is 0. So all I need to do here for number 11 is do the derivative of the 5x. So it's just a 5. Because the derivative of each of these other 3 pieces is 0, 0, 0. The derivative of each constant is 0. So we get for number 11, it's just 5. And let's see, is there more? Oh, there are just a few more. So let's keep going here. 3 more. This tangent to the 9th of x, do you remember the way we could think of that? Is tangent of x to the 9th power. So for number 12, the outside function is the tangent. So we're going to do the derivative of, oh, I'm sorry, wait, don't let me get away with that. Sorry about that. I'm jumping ahead. The derivative of the outside, or the outside function, is the something to the 9th power. So we want the derivative of something to the 9th power. And then we're going to multiply that times the derivative of the inside function, and the inside is the tangent. So the derivative of something to the 9th is going to be 9 times that something to the 8th, and that something, the thing that's raised to the 9th power, is the tangent of x. So we're going to have 9 tangent of x to the 8th power times the derivative of tangent is secant squared, because I can think tangent, secant, tangent. Go in reverse, that would be the derivative of tangent is secant. So it looks like we've got 9 times, let me write this in the proper format. 9 times tangent of x to the 8th power times secant of x to the 2nd power. And you can find that answer here. Right in the middle there. A couple more. Number 13. For number 13, we've got cosecant of x squared. So the outside function is the derivative with respect to x of cosecant. And the cosecant of what? Of x squared, right? But it doesn't even matter what that something is. It's just that we're going to do the outer function is the cosecant. We're going to multiply that by the derivative of the inner function, and the inner function is the x squared. So the derivative of cosecant, and remember, let me write it up here. When we're using the trig derivative rules or formulas, however you want to think of them, you could do the opposite of the secant, right? So I was thinking secant, tangent, in the same way I could say cosecant, cotangent. But remember that the derivative of a co is always the opposite. So we've got the opposite of cosecant, cotangent. The derivative of cosecant is the opposite of cosecant, cotangent. Cosecant of what? Of x squared. Cotangent of what? Of x squared. And then the derivative of the inner function, so the inner function was that x squared. Derivative of x squared is 2x. I could make this look a little bit better by bringing this 2x as a coefficient out in front. So it would look like this. We've got our negative, or our opposite of 2x cosecant of x squared cotangent of x squared. And you can find that answer in the answer box there to verify, yep, we've got it. And then one last example, number 14. You know what is going to make this really easy? We're not even going to need the chain rule. If I just rewrite this as a power, I'd have x to the -1. And the derivative, using the power rule, -1x, be really careful here, because it's the exponent is going to be -1 minus 1. So 1 less than -1, 1 less than negative 1 is negative 2. So what do we have here? We've got the opposite of x to the negative 2. And I'm going to put this in a format that doesn't have a negative or rational exponent. So I could simplify this to be 1 over x squared, because that negative 2, x to the negative 2 means 1 over x to the second power. And then don't forget this negative out in front, right? So we get the opposite of 1 over x squared, which is right here. Well, I hope this video has helped. Let me know if you need more assistance with any of these examples.